Well, I think we're going to go ahead and get started here, everyone. We got a lot to cover, so more people will be joining us. Welcome, everyone. My name is Scott Bradley, and I'd like to thank you for attending this week's webinar on computer-aided manufacturing. In this session, we will take a look at the intuitive and powerful integrated CAD-CAM solution, Inventor HSM 2016, and how it is revolutionizing the CAM industry. With truly integrated CAM, we capture and update all of our design data with a seamless workflow while simplifying data management. In addition, we will introduce the concept of the technology consumption gap. Next week's session will cover controls, electrical, engineering, and design. So we encourage everyone to go ahead and read the session and attend. You can see that at http d3tech.net/D3VU on our D3Tech.net website there. You may have questions as we go through the session. At the end, we will provide a means to get your get your questions answered. A brief word about D3. D3 is the top integrator for Autodesk manufacturing solutions, offering a wide range of products and services to help our customers design better, manufacture better. Some of the services that we offer at a glance here: we do have training, both public, private, individual, and our new corporate training plans. Of course, our support, phone, chat, and email. Our mentoring programs, one-on-one, general questions and answers, and project consulting. We do implementation, best practices, consulting, as well as automation of engineering, design, and sales. For our presenter today is Nick Narzinski from D3's technical team. And at this time, I'd like to introduce our presenter, Nick Narzinski.
Thanks for the introduction, Scott. All right, our webinar today will be based around mechanical engineering and design. The webinar coordinator introduced you to a theory called consumption gap. The book Complexity Avalanche shown here defines the consumption gap as the difference between the potential value of a product could provide to an end user compared to the value it's actually providing today. In the book, J.B. Wood identifies the curve shown here as the addition of features and complexity seen in technology products in the last several years. This technology not only relates our topic of engineering software that we will be discussing here today, but also industries such as cell phones, automobiles, and even televisions. The lower curve shown here shows the trend of end users to consume the features being offered without assistance. This is where D3 can help to maximize the value you are receiving from the software you currently own today. So D3's goal today is to help minimize the consumption gap by showing a few workflows and tools that we believe are currently being underutilized or not being used at all. These topics include integrated CAM, so the workflow of working inside your CAD environment on programming your parts for CAM, then adaptive clearing, taking advantage of high-speed roughing technology, using 3D toolpaths on prismatic parts to speed up your workflow and reduce setup time, and then turning or mill turn, which has been introduced with 2016 HSM. So let's get into the software. Here we see Inventor 2016. So I think a lot of you will be familiar with this. For those of you who don't know, this also integrates into SolidWorks and it matches the interface of SolidWorks. But today we're going to be working with an Inventor. And as you can see on the ribbon, we just have a new tab in here called CAM. So this is where you're going to find all of your job setup, simulation, tool paths. You can see it's broken down by panel into 2D, 3D, multi-axis, and turning. So this is all being done right now on a part file. What I'm going to do is drop this into an assembly. We can constrain it within a vise and then actually program it in that environment. That way we can take into our simulation and collision detection the fixturing that we use on our parts. So here I actually have a template set up where I dropped our vise into, so I just called orangevice.iam. So as soon as I start that template, I already have my fixture in there. I've even got a constraint to where the jaw just slides along. So all I'm going to do is, let's just copy this part from that part file and place it into my assembly here. And then with that, then I can use my relationships to constrain it in place. So I like to use constraints. Joints are a fairly new addition to Inventor. So another consumption gap that might be out there is using joints to speed up your workflow. So what I like about this is they have one called rigid, which with just a few clicks you can constrain a part in place. So I'm going to use rigid here and rotate to the bottom of the part, and I'm going to use this. You can see here there's a series of dots on here, but I'm going to select this point, and I want to lock that in place with this point right here. So you can see it shake there. It gives you a little preview telling me that it's rigid. All I need to do now at this point is flip that. There we go. And then I can give it an offset. So I'm going to raise it up 0.02. So you can get a little bit of room there to run the tool down the side of the part. So pretty easy. Use joints. With just one joint, that part is now locked into place. You can see there next to my cursor, it's completely constrained. So then the last thing would be just to constrain my movable jaw here. So I'll come in and just do a simple face-to-face constraint this time. So with our part in place, now we're ready to move over into the CAM environment. So first thing I'm going to do is a job setup. And within here, you see it finds the entire assembly initially. I'm going to tell it I want to work on this model. And then I'm going to reorient my work coordinate system. So they made it really easy in the software. So right now you can see it's matching the work coordinate system of the assembly. All I'm going to do is select the stem here of the z-axis. That allows me to select an edge I want it parallel to or a face I want it perpendicular to. It'll rotate that z up into your spindle. Then I can move that by selecting stock point here in the browser and choosing a point on my model. You can even use a selected point. Maybe use a point off your fixture. That way you can reference the same point over and over again. And then once you got that in place, then we can move to our stock tab. Here's where we define what size stock we're going to start with. So we can see what our finished model is. One of the options in here is from solid. So if you have like castings that you're working with or something that's not a cylinder or a rectangle, you can actually model up your solid and use that and just select it. But for today, we're just going to use a fixed stock size. And I'm going to go with 4 1/4, or 4 1/8 rather, in the X, 3 in the Y, and 3 in the Z. And then I'm going to throw an offset value from the top of the stock to 0.01. So we got some material to face off in the top. So now you can see, oops, I didn't want the on the sides. Where is, that'll be my Y depth. And I went ahead and hit escape. Let me just do that again real quick. Let's show you how quick it is to actually do it, but you can just select the setup. Selected point, stock, 2.5. It was actually the right size to start with. So what I really wanted was 4 1/8 here. And 3 here with an offset from the positive 10,000ths. There we go. And then the last tab here is post-processing. If you guys have multiple vice setups inside your mill, you can set that up here, do multiple offsets, enter the number of duplicates, and then you can actually preserve that to post out by order, operation, or tool. So let's say you have 4 vices set up. If I do it by tool, it'll actually post out to come in and face off all 4 parts before it switches to an end mill, for an example. But in this case, I'm just going to use the G54, so I'm going to go 1 here and OK that. So now we have our job set up, and we're ready to start adding operations. And the first thing I'm going to do is a 2D facing operation. So I'm going to come into my tool library. As you can see, these 5 tabs for this operation, these are the same 5 tabs for all milling operations in the software. So they made it really easy to learn. You go tool, then your geometry, then your heights, passes, and linking. So same workflow for almost every operation. So it makes it really easy and intuitive on learning the software. But as I mentioned, we're going to go into the tool library first, and I can do a search and find all my tools. I've already got them set up inside that part file, so I'm just going to select the face, select that. So here's our face mill, and I'm just going to right-click and say OK. They did a really good job at defaults in the software. So by default, facing operations are going to come down, lead in outside the stock, and make its passes based off the diameter of the tool and the width of your stock. It's going to make all the passes directly on top of the model. Now, if I wanted to, it's really easy to come back in, edit that operation, and on the passes tab, you'll see here you can add multiple depths or change your step over. But they did a really good job with the defaults. And let's rotate back. And then the next one I want to do is rough this part out. So I'm going to use a technology called adaptive clearing. This is our high-speed roughing technology. And before I get into it, though, I want to, well, let's just program it and see what it looks like, and then I'll dive into what exactly it's doing. So if I go in here, select my tool, and I'm going to use my 3/4 inch end mill. Move to the Geometry tab. Here you can see it's looking at a boundary. Right now it says none, so it's going to default to the stock dimensions. So that's what that yellow box represents, as the outside of the stock. And it's going to machine within that, recognizing what my model is. So on the Passes tab here, I'm going to go down to, the heights tab, I'm going to go down to Model Bottom. So we're not going to go, as you can see here, the Model Bottom is just a little bit above my fixture. And you maybe even want to go a little bit past. You can click and drag these planes around. So editing your heights is really easy in the software. And in the Passes tab, here we can see optimal load. This is a load based off of the chip load of the tool path. So as it's cutting through, you set your optimal load there. And then down here we have maximum roughing step down, which I've got set to 10% or 90% of the flute length. So we're using the full length, almost the full length of the flute, and we're taking a shallow pass as my step over. So let's take a look at what that looks like. Here you see it calculating. All right, so it's going to come down at the deepest point it can and make its passes. And we can simulate these at any time. So let me just select the setup and go to simulate. So there's the facing operation. And so here, you can see it starts at the deepest point of the flute length it can make. And then it's going to work upwards until it hits a flat area detection. Here we see it working at that flat area of the step down. And again, this is based off the chip load, so we're taking a consistent step over at all times. So the principle behind adaptive clearing is shallow step over, but full length of the flute. So we're actually using the cutting edge of the tool as opposed to traditional milling. And then we have little stair steps left behind based off of the parameters that we set inside the operation. So I got a couple other parts here just to show the advantages of adaptive clearing. So here in this one, this is a tool path like traditional milling. We're taking the full diameter of the tool, but we're taking multiple step downs. So we're really limiting our use of the tool by only using the end of it. So as I simulate this, let's go ahead and play that. So here you can see it coming in, and we have a very inconsistent load on that cutter as it's going through. Here we have a little shallow pass, and then here, let me pause that for a second. If I turn the tool off, it will still be able to see the path. But as it's going through, you can see we almost get a full tool engagement, then a half tool engagement as it comes back out. So there's no way to limit when you have internal corners like this how much of a step over it has. When you set your step over, it has that step over, and it's going to continue that throughout. But what it doesn't have the ability to control is, with that step over, how much actual stock is being engaged with the cutter. So this is where you find that inconsistent sound. You'll break tools by doing this. And again, it takes more time because we're having to do a lot of step downs to keep the load on the cutter to a minimum. So with the adaptive clearing technology, we'll look at it again. This one, we're taking shallow passes, but we're always taking a consistent load onto the cutter. So as I simulate this one, you see it starts on the outside and works its way in, always with the same step over. I'll turn the tool back on. Using the full length of the flute. By doing this, the heat's being removed with the chips, and we're actually able to preserve or lengthen the tool life of the length of your life for your tool. And then I wanted to point out also, once it gets to the end, speed this up a little bit. Here I wanted to show, once it gets down to internal corners, you can see here the step over, because there's more surface area on the tool, it actually takes shallower passes. So we're keeping a consistent load on the cutter at all times. And so that was that part, just showing a comparison between traditional and adaptive clearing. Here we have a part, a 3D part, where we are able to, again, I could do just the outside and work to it and then add other strategies like 3D milling, or you can rough out the bulk of the material with a large tool. Get that turned off. There we go. And here we have flat area detection turned on, so that's just a setting. If I go back and edit that tool path, we have flat area detection, so that's automatically going to create passes at flat areas. So like right here, we have flats, and on these steps, we have flats. So here you see it work from the outside and work its way in, and then we're going to cut. We're always going to have a pass because we have that flat area detection. It's aware of the model and the software, and it's going to create passes at those flats, maximizing our cutting time. Then you can also do order by depth, which, as you can see with order by depth turned on, it's just going to work its way from the outside and then back up. So if I simulate that. So here, it does the maximum flute length, and then it works its way up. Now with that, you're getting a lot of rapid movements once we get to this point, going back and forth between the two sides. So another nice feature in the software is we have the ability to order by area. So that's what this next one is here. Order by area, and with that, we can see there's really only one movement. Once we get down to this depth, there's only one movement, and that's because it's ordering by area. It's going to machine this side, and then it's going to move over and machine the other side. So you have lots of good options in there to really minimize the rapid retracts and keep that tool engaged with the part or with the stock. So hopefully that gives you guys a good understanding of what adaptive clearing is. And for those of you with older machines, you might be asking, what does this line of coding look like? Is my memory going to be able to handle something like this? We do have a parameter in there called smoothing. So with smoothing, you're able to limit the amount of point-to-point tetrahedral tool path or movements that tool makes. So in here, if I go back into one of them, here we have the smoothing. If you turn that on, you can change the tolerance down and really limit the amount of code that operation creates. And then we even have a parameter in here to limit the amount of stay down. So if I go, the last one I'm going to show you is this one here. So here we have a stay down level. So this is the amount that this tool stay down as it calculates tool path to least. With that, you see all the retracts that the tool is making here. Now, retracts aren't necessarily a bad thing. A lot of times it's a high-speed movement. You're coming back around. Sometimes it's even faster to do the rapid all the way up to the retract as opposed to something like the most here. So this one has the settings for linking to the most. And with that, here you can see the tool really stays down the whole time. And so if you want to see that in action, I actually have a video of us cutting this part here. And so here you'll see it actually cutting without coolant on, because we're able to remove the heat on those chips by taking that shell pass. So it's being transferred directly to the material. And I'll let it get here to the rapids real quick, and then I'll jump back over to our part. So here you can see it just lifts up. I've got it set to, I think, 10 thousandths. It's coming back around and making those movements. So maximum depth of cut, shallow passes, really reducing machining time and maximizing our tool life. Okay, so back to our problem now. We were working on this part here, so we had the facing and then our adaptive clearing. And so the next one I want to do is a finishing pass on the outside. So I'm going to do a contour. I could do 2D contour and then make a bunch of selections and tell the tool where to go. But with 3D contour, the software recognizes our actual file. So I'm just going to do a 3D, switch to ½ inch. This is going to be my finishing end mill. And my passes tab here, I'm going to change my step down to the tool flute length. And all of our operations are parameter driven, so I can use the parameter tool flute length from my tool that I created. Hit enter, it's going to pull that parameter in. I can right click and make that a default, or edit the expression of what controls that parameter. So the software is very customizable. All right, so let's take a look at what that looks like. What to do wrong here? Tool center, do tool outside boundary. Climb milling. Oh, that's close. Now I just need to go back into my linking tab. So you can see how easy it is to work. Go edit, see what the toolpath looks like, make your edits as you go along. But here I'm going to change my helix to plunge. All right, so there's our finish on the contours. And then I'm going to do a finish on the flat here. So we have one called horizontal. This just finds all the flats inside my part file. I'm just going to OK that with the defaults. Here you can see it's trying to machine the top, which already faced off. So I can go back in there and turn on the heights tab and just drop down my top height. Oop. Didn't mean to grab that one. I just want to move my top height down to below the top of the part. And there we have a finish on that flat. And then the last thing I need to do is finish this angled face here. Now we could do this as a 2D setup, open the doors, come in and create a fixture for this, turn the part sideways, and come in and machine it with a flat. What we can do with 3D milling operations is really reduce our setup time and just do a 3D operation to come in and clean up the rest of that material, because right now we're left with a bunch of stair steps behind. So let's just simulate real quick to see what we have. And here I might do an order by area, so it's not jumping back and forth on that adaptive clearing operation. So that's what we're left with. We just need to come in here and clean it up. I'm going to use our parallel strategy for this. Come into my tool library, use a ½ inch ball mill. Select geometry tab, so we're going to tell it where to cut. I want to cut not what's inside there, but I want to limit it to this face. So I'm going to select that again, and then I can just kind of trace out what I want that boundary to be. And then hit the check mark, take a look at it from the top. All right, so that looks good for my boundary. And then come to my passes tab. Here I can set the angle, the direction. It always goes with the X direction, so I'm going to make this 90 degrees to my X direction so I can go up and down. And put a nice fine step over. Let's do 10 thousandths. And then let's do tool outside boundary. And down here we have a area to do avoid or touch surfaces. So I'm going to tell it I want to avoid overlapping the part and just select all these faces around it. That's going to ensure, because I did tool outside boundary, that's going to ensure that my cutter doesn't make contact with anything else. There we go. So there we have a finishing pass on that face. Now we can do a setup, select the setup again, run through simulation. And once that's done with the 3D package, you also have a show part comparison here. And then you can also see the true feeds and speeds and the timing of the operation here on the info tab. But I'll go back here to the display tab and turn on show part comparison. And here, anything that is blue, like we see down here, dark blue, means that there is material still left to remove. Anything that's gray means we machined to the surface. If we had anything that was red, that would mean we actually overcut the part. And I have a fine interval turned on here, so we see a little bit of blue on the surface. That's just all the little cusps that are left behind the ball mill here. So that part's now finished. We can save that. Your operator is going to need to know what tools to load, so I can go in here and select post-process, or I'm sorry, select the setup sheet. This is going to post out just a breakdown of all the information for this job. So here we can see the file. If I had it saved, you'd see the location, what stock to start with, and then we have a breakdown of each tool, what tool holder to load it into, your minimum and maximum Z values. So a lot of good information in here for the operator. And then we're ready to post-process. So here I can go to Setup, Post-Process, and there are, let me change back to the generic posts that come with the software. Last time I counted, there was 82 different post-processors that come in here. For standard machines, you can just find the one for your controller or machine. I'm going to use just a generic Haas. And there's some different parameters you could change down here to edit the post, like if your tool or if your machine has a swing arm versus an umbrella tool changer, you can turn preload tool on or off, different things like that. So I'm going to post this out, and the software comes with an awesome post-processing editor called HSM Editor. And here you can see where we're cutting, where we're retracting based off the color. You can jump around between your tool changes, so good for navigating. You can come in and transmit. If you guys have an RS-232 hookup, you can do DNC stuff. You can also run a backplot in here directly off the G-code. So if I turn the backplot on, we can run through line by line a simulation of the cutting. So a lot of powerful stuff within here. And you're going to load that in the machine and cut the part. And then you flip the part over and probably have to face off the bottom material as well. So that was that one. What I wanted to show real quick is another neat feature in the softwares we have is templates. So we can save multiple operations from one part. It's going to save all the parameters for that operation as well as a tool, and we can drop that onto other parts. So here I'm going to save the face, my adaptive, and the horizontal. And I'm going to make those a template. So I'm going to store this template here and just call this prismatic. You can see I've done this a couple times. Parts. And come back. I've got another part here. And I'm just going to simply, let me duplicate this. Actually, let's just create a new one. We'll do a setup. That's easy to do. No need to duplicate. Select the Z, the face I want it perpendicular to. I could select the stock point, choose a point on the part that I want to move that to. And I didn't show you earlier, but you can easily flip these two by selecting the arrowhead of the different X, Y, or Z coordinates. Then on my stock tab, I define a stock. So I'm going to do relative size box. Well, let's keep the defaults here. So we got a setup and then I can go down, right-click, do create from template. There's my prismatic parts. I can do create all templates or do just a single operation. You'll see a bunch of red X's here. All I have to do is select the setup and click generate toolpath, and it's going to update all these toolpaths to my geometry. Now with the 3D operations, we don't have to make any geometry selections because it recognizes the model. So this will really speed up your time for those simple prismatic parts that you guys do. So there you can see a finish on the flats, our adaptive, and our facing operation. Oops. So then you can simulate, verify, and post that code out. Or in this case, you might go in there and edit the model just to take care of these corners are left behind. Maybe you put in just a cutout so that you could fit your tool in there and actually machine that entire thing. Maybe you're a part that needed to slip into this area here, and we needed those corners gone. I can create just a cutout there. Let's go ahead and do that actually. Easy enough to work between the model and the CAM environment. So I'm just going to select the face here and come in. I think there's a 1/2 inch flat that I used to do that horizontal. So I'm just going to project those two edges. Let's draw a circle at 0.26 diameter, just a little bit more than it's a 1/2 inch, make that 0.51 diameter. So I need that to be just a little bit off here. So I'm going to draw a line that goes to the part, constrain it so that it's on that edge, and then I'll just dimension that so that it's centered. So put 45 degrees there. Finish that. I can then come back to the Model tab, cut extrude that, and so that's cut, and I want to go to a selected face. I want to go to this face and check that. So now we got some room for my end mill to come in and actually create clearance so that maybe something can slip down inside there. And I would need to mirror that over, so I'm just going to do a simple mirror. So mirror feature, I'm going to select my cutout that I just did and go to mirror plane, and then come back to my model environment and select the plane in the center of the part because I drew it centered, and hit OK. So now we got that on both sides. Move back to my CAM environment. You see the red X's here again. Remember what we need to do there? Just select CAM, generate, and it's going to update those tool paths. So now you can see my tool comes in there, and we're going to have a nice finished surface in there. If something did slip down in here that was, had a sharp corner, it would now fit inside of that area. So really easy to work back and forth. You can also use sketches to control tool paths if you needed to. So there's just a little bit on 3D milling in the software. One more thing I do want to take a look at before I let you guys go today is turning, which was newly introduced with 2016 in Inventor HSM. So here you can see our turning operations. And I have a part here. Let's take a look at that. So here you can see it might need some turning work and maybe milling work, or if you had a turn mill machine, you could use that. I've already got a job set up in here. You guys have seen that, so we don't need to go back into it. But if I do edit here, you can see my operation. Instead of milling, I did a mill or turning. And I have my coordinate Z on the front of the part. Then we have a stock tab here. I got a fixed cylinder, so we got fixed size. We got some stock on the backside to grab off to on the chuck. I do want to check this box here for spun profile. What that does is if you have a part such as this that does not have a similar rotational profile throughout, things like this cutout here, it will recognize that as what the spun profile needs to look like, so we can do all the operations in turning and not cut into that area. So we can get so that spun profile gives us a profile that we actually need to turn. Then you can later on do anything with the mill work or the turn mill. So within my setup here, can't get it to show up. So we turn, our first thing we're going to do is just face off. So I'm going to select the facing operation for turning. Come into the tool library. And I got a face tool here. So I'm going to select that. And again, just like the milling operation, it automatically works to the front of the part. So I'm just going to right click and OK this. And there's our facing operation. Next thing I want to do is profile the part. So I'm going to do a profiling operation. And I'm going to use the same tool. I'm going to do outside profiling from the front to the back. Move to my geometry tab. Here I'm going to do a confinement. Maybe I want to go a little bit past the back of the part. So I'm just going to select that surface and that surface to confine it between those, but with a back offset of, say, I don't know, 2 millimeters. And on the passes or the radii tab you see here, it works the same as milling also. You can click and drag your different planes around. So you got your inner, your outer, and your clearance. Now on the passes tab, I don't want finishing passes. I'm going to come in with a different tool and finish this up. So I'm going to uncheck finishing passes, and let's see what that looks like. All right, so there we have it coming past the part just a little bit, and I didn't want to do machining on the front of the part again. So I'm going to uncheck allow grooving here. That's going to keep it from going down inside this area. And on the front of the part, I don't want to machine that again because we already faced it off. So I'm going to come back in and turn on rest machining. That way it recognizes what's already been faced off. So easy, again, to work back and forth between, your tool path and coming back and making edits. Make it real intuitive from running software. So there is my profile. Now I want to do a finishing pass. So I'm going to do the same thing. I'm going to derive that. We haven't looked at this yet, but you can carry over the selections from one operation into another. But I'm just going to do a carryover into another profile, but this time I'm going to use my finishing tool. Select that, outside profiling, same confinement, rest machining turned on again, so it carried all those parameters that I set in the previous operation over. The passes tab, I don't want to do any more finishing passes or any roughing passes, but I do want to do a finishing pass. And let's give it a, let's hit OK. See what that looks like. So there is our, didn't need rest machine turned on. There's our finishing pass. And then I want to do a roughing inside, or roughing and finishing operation inside this area here. So I'm going to do that with the grooving. Select grooving. It automatically defaulted to my grooving tool that I had in here because it only allows grooving tools for this operation. So I'll select that. I'm going to do outside grooving, front to back. Geometry tab here, I'm going to do a confinement between these two areas and turn on rest machining. And then on the passes tab, let's see, I've got up and down. We've got finishing passes and roughing passes turned on. I'm going to make my step over like a 0.1 for my finishing pass. So there's our finishing pass on the grooving operation. And the last thing I'm going to do in the turning environment is drill out my hole here and then do a turn boring operation to finish the inside. So just come to my drilling operation. I've got a 14 millimeter drill bit. Select that. Go to Geometry tab. I'm going to select my hole faces. I want it to go through this face and this face. And I want it to go all the way through the back of the part. So I'm going to go to my Heights tab, select, instead of hole bottom, I'm going to do a selection. Select the bottom of that part. It gives me my plane there, and then maybe drill tip through bottom. That's going to ensure that the tip of your tool breaks all the way through the back of the part. And then I have an offset value set there as a default. We go just a little bit past the back of the part. So there you can see the tool, or tip of the tool is going to come all the way through. And okay that. And then the last but not least is an inside boring operation on here. So I'm going to go do a profile, come to my tool library. I've got a boring bar. Select that, and here you can see my orientation is a little bit off. I need to rotate that tool. I'm going to go to tool orientation, rotate it to 90, so we can slip it inside that part. And I want inside profiling. Front to back looks good. Geometry, I'm just going to let it go through the whole part. Passes, let's do another fine step over 0.1. Oops. And okay that. And I didn't turn on rust machining, so you can see here it's trying to machine it again. If I tried to simulate this right now, it would give me a crash going in there without the drilling operation. So let's go back and turn on rust machining. There we go. So again, it's always aware of the stock as it's going through. That's the beauty of the 3D and turning within Inventor HSM. All right. So now we're done. Go ahead and select that setup and run through the simulation. Got my stock and tail, tool path turned on. Go ahead and play. There we go. So here you can see, and again, I can go to the info tab and see all the information for that operation. But here's our finishing passes on the outside profiling. Our finishing pass, then our grooving operation. Our drilling, and then our finishing on the inside of the part. There we go. Might need a little bit longer boring bar. All right. So with that, then you can see the part comparison here. So look, gray and statistics here. You can see a full machine time. We haven't taken a look at this tab yet, but it's going to take approximately 4 minutes, 57 seconds. That's a pretty accurate time you can input into the software. If I can click the right thing. There it is, machine time. So I can come in here and input what our tool change time is. So you can see your tool change time, and you also can input your rapid feed rate, and that will give you a pretty accurate machine time. So once you're done, then you run through that setup and posting process again. So there's just a few, if I can pull that slide back up. There we go. So using integrated CAM, we're able to go back and forth between the CAD environment and the CAM environment, update our tool paths, taking advantage of our CAD models, all within one solution. And one thing I didn't mention is all that's done within one tool path. So all the stuff that's being done on this part is all being done on that tool path, or on that part file. So it's all saved in there. You're not having to worry about file management and having 2 different files floating around out there. And then adaptive clearing, we took a look at that, maximizing our tool life, cutting parts faster, 3D tool paths on prismatic parts, so using those 3D tool paths that recognize the geometry of your model, really reducing cycle time and setup time, and then our new addition of turning and mill turn into Inventor 2016. So hopefully you guys got something out of this presentation, and I'm going to turn it back over to Scott for closing here.
Thank you, Nick, for that informative presentation there. At this time, I'd like to provide 2 brief polling questions, and they should pop up here for you. real quick there. And also, make sure you guys go to d3tech.net and look at our D3 Virtual University page and see what other classes that we have coming up here in the near future coming up in September and later on in the fall as well. So we'll just give you another minute or so here to finish up that first question. All right, now let's move on to my second question here. And like I said, our next event is coming up August 25th, and that is the Controls, Electrical, Engineering, and Design class that's moving on the 25th. We'll give you just another minute or so to finish up this last question. Okay, and that concludes our session for today. Thank you all for your time and attendance, and we look forward to seeing you at the next D3 Virtual University session.